Today we are going to continue our work on determining what graphs of polynomials look like and what different characteristics help create the shape they are. We're going to go more into depth as we did compared to what we did in 811. 811 we just started it. Now we're going to keep looking a little bit more. So before we get into it, go through each of these and draw in the air with your finger, or if you really want to, just sketch on your paper, no x and y axes, what the graph of each of these looks like. Okay, so for the first one, it's cubic, and there are 3 different x-intercepts. My a value is positive, therefore it's going to look something like this. Okay, or even if you want to see it a little bit more in depth, it looks something like this. Okay, so that's the first one. In the second one, this is a 4th degree polynomial. So in a 4th degree polynomial, it does have a positive orientation, so it comes up this way, here, here, and like this. So that's my 4th degree polynomial. In C, C in green here, or R of x, that's a 4th degree polynomial, but now it has a negative orientation, so it goes this way. And it crosses my x-axis possibly those 4 times. The next one is a 4th degree polynomial, but now this one has 2 repeated roots, and then also it has a positive orientation. So this one is going to bounce on the x-axis at those spots, but what it looks like without the x and y axes is actually very similar to that second one. And then the last one, that's our 5th degree polynomial, I think 2, 4, 5, yep. So our 5th degree polynomial with a positive orientation goes 1, 2, 3, 4, 5. So I was just trying to visualize where that x-axis would sit so that I got those 5 intercepts. Okay, so again, just building off of what we did the other day. So now, in today's lesson, we're going to take a look back at what we finished before, and we are going to look at roots. Remember, those roots are those x-intercepts, when they're real, of polynomial of degree 3. So what's the maximum number of roots that you had if it had a degree of 3? It was 3, right? So an example could be something like this. So if it had degree 3, there would be 3 roots. If it was degree 5, there would be 5 roots. And that's the maximum number. So therefore, it's degree n. How many roots do you think? N roots. But can a polynomial have degree n with fewer than n roots? So for instance, if we had a cubic, could it only have 1 root? If we had a cubic, could it just have 1 root? Yeah, it just crosses the x-axis at that one spot. That has 1 root. So could a degree of n have fewer than n roots? Absolutely. They could be repeated roots, which is this example, or it could be shifted, which would be this one. So absolutely. So we need to be careful. Just because we only see it crossing our x-axis a certain number of times doesn't mean that is the degree of the polynomial. Okay, but we know it can have up to and including that many roots. So in this example, for each of these polynomials, state the minimum degree its equation could have. So look at the roots and figure out what the minimum degree is. Go ahead and go through it. 3, 2, 4, and 5. Feel free to draw through that axis, and then you can count how many times it is. Now remember, if it's shifted up or down, it might not cross the x-axis, but we can get an idea of what the degree is at least. Which of the graphs above show that as the x values get very large, the y values continue to get large? 1 and 3. How would you describe the graphs of the others for as x gets very large? So as x gets very large for this one, as x gets big, y gets small. Right? So as x approaches infinity, that means as x gets large, y approaches negative infinity. Think about it as n behavior. Your y value decreases. And this deals with that orientation which I've been talking about. So when the y values of a graph get very large, as the x values get large, so as x approaches infinity, y approaches infinity, the graph has a positive orientation. So as x approaches infinity, y approaches infinity, that would be a positive orientation. And you may want to add this into your notebook. But as x approaches infinity and y approaches negative infinity, this is a negative orientation. How is each of the above graphs oriented? Therefore, we know above 1 and 3 have positive orientations. So the first and the third have positive orientations, and the second and the fourth have negative orientations. The orientation is based on as x approaches infinity. So it's always on the right-hand side of the graph, which is why when you've seen me graph all of these, I always start on the right-hand side and I work my way backwards because I know the orientation. So the next one. For each graph in 828, so the previous problem we just did, you decided what the minimum degree of its equation could be. Under what circumstances could graphs that look the same as these have polynomial equations of higher degree? So that's what we're going to be looking at here in this problem. So consider the graphs of y equals x minus 1 quantity squared and y equals x minus 1 quantity to the fourth. How are they similar? How are they different? Take a moment and pause the video and go ahead and put these into your calculator so that you can see these. So how are they similar? They have the exact same shape. Exact same shape. But how are they different? This one flattens out more. At x equals 1. And then also what ends up happening is it grows quicker as well, or it rises more quickly. Look at the equation from 2 from the previous problem. So we're going to look at this here. Could the equation for that graph have a degree 4? So right now it has a degree of 2. So that's what we said. Minimum degree is 2. Could it have a 4th degree? Absolutely. We don't know just by looking at the shape of the graph. We know it could be 2. We assume it's as small as possible. It could be 6. It could be 8. It could be even. Could have an even degree. They all have that parabola nature to it. So absolutely it could be a 4th degree. But could it be a 5th degree? Absolutely not. What do you know about odd degrees? This is an odd degree. This is an odd degree. Think about a linear. It's the most basic odd degree. It looks like a line. This does not look like a line. Its end behavior go in the same direction. Versus odds, their end behavior go in opposite directions. Okay, so looking at how is the graph of y equals x cubed similar or different to the graph of y equals x to the 5th? Very similar piece as before, has the same shape, and if you look at wherever that value is, so in this case it's at 0 is where it's crossing my x-axis, it's going to flatten out there, and then it's going to grow really quickly, and it's going to get, in essence, it looks narrower from there. So how do the shapes of y equals x minus 2 cubed and y equals x plus 1 quantity to the 5th with repeated factors differ from the shapes of equations that have 3 or 5 factors that are different from one another? So polynomials with different factors have different relative mins and maxes, and not just bends. So we're going to be looking at each of these pieces. We're going to look at where the x-intercepts are. They're going to look a little bit flatter. But if there's only one of them, so if there's only one root, it doesn't have that relative max or min. It doesn't have, like, so here's a cubic. This has that min and that, or this max and this min, whereas this one here has this piece here. So it has that flattened out part versus the big humps, the big, like, swirls up and down. So that's one of the big differences that you're going to look at when you have repeated roots or repeated factors. Okay, we'll go back to our single page. So in 30, we start talking about these double roots and these triple roots. So in the first example from the polynomial function, so from yesterday, you had the following equation. And we know x plus 5 squared is a factor. That squared factor produces double roots for the function. Okay, so that's going to be called a double root. It would be a linear factor otherwise if it was to the first, like x minus 2 is a linear factor. So if there is a double root, or if there is a root to an even power, graphically what you're going to look at is what? What happened here? There's a bounce there. So you have a bounce at -5. So you're going to be looking at that bounce. It's going to then turn back around. It's tangent to the graph there. It just touches it and turns back around. Versus if you have a triple root or a fifth or whatever it happens to be, the triple root is still going to go through. So odd roots are still going to cross through your x-axis. It's going to flatten as it passes through. As it passes through the x-axis at this root. So when it's triple roots or 5 times or what have you, it's going to cross through. It's not going to bounce. It's not going to be tangent. It's going to cross through, but it's going to flatten each time that happens. And again, the higher that exponent on there, the flatter it gets. Sorry, that was the wrong one. We did that for our warm-up. Okay, so with these last 3 problems, so this is 35. With these last 3 problems, what I want you to do is, without using a calculator, I want you to graph these. I want you to make an xy axis on here. I want you to put your x-intercepts, and I want you to figure out your orientation. If it bounces, if it goes through, make sure that we see that as well. So pause it right now, and I will do each of these for you just to make sure that you have it solid. So in the first one, when I look at all my zeros, I have a 0 at 0, I have a 0 at -1, and I have a 0 at +3. Clean that up. Try that again. -1, 0, and +3. And then if you look, you see this negative here, which means there's a negative orientation, which means it's going to come up from this end. Up here, come down here, and then it's back up to here somehow or another. Okay. In the second one, I have zeros at +1, at -2, and at +4. I also know at +1, it is going to bounce. So +1, it'll either look like this or like this. What I do know is that I have a positive orientation. Therefore, it's going to come through here, and then it has to bounce, and then come back through here. So that's a 4th degree polynomial. So it kind of looks like a U. And then the last one, that's a 4th degree polynomial. I have a 0 at -2. I have a 0 at 4. And at -2, it is a cubic. So at -2, it's either going to go through this way, or it'll go through this way. Just depends. So when I draw this, it has a positive orientation, therefore it comes through here. Comes through, makes that cubic shape, and then goes back up. So one last quick piece for this. This is a 3rd degree polynomial. This is a 4th degree polynomial, and this is a 4th degree polynomial. If I ignore the whole middle, do you see how this could kind of look like a line if I connect them? It's because it's odd. Versus here, if I ignore the middle, do you see how I could make a parabola shape with that? It's because it's even. And the same thing here. This looks like a parabola because it's even. So looking at the degree will give you an idea too, based on what happens at the ends. Again, that's end behavior of these. But back to our pictures so you can see what they all look like. Okay, so we're one step further to being able to graph polynomials based on characteristics that we know without using our calculator.